So a little bit of a recap of what we did yesterday in example 1 before we go to example 2. We said if we looked at y equals and then a sine b x minus c plus d, that would be all the transformations from our transformations unit built into 1. And what we're going to do throughout these examples is look at the different values and what they do. So in example 1, we looked at what happened when we changed that a value. And that a value, what we noticed for a regular sine or cosine graph is it changed the amplitude. So our amplitude is normally between 1 and our range is between -1 and 1. Well, now that we have a 2/3 in front, now the maximum is at 2/3 and the minimum at -2/3. Or with a -4 in front, the maximum is at 4 and the minimum is at -4. And that negative in front meant that your graph was also reflected over your x-axis, so it started at -4, started at a minimum for cos, rather than starting at a maximum. In example 2 here, now we're going to look at what happens with the b value. So our b value, normally that was something that happened horizontally. It was either a horizontal compression or a horizontal stretch. And if we look at the 3 examples here, can you see that the cos 6x in part A, that would be a horizontal stretch or compression? Compression. We would multiply by 1/6. And in B, where we have the 2/3, it would be a horizontal stretch. We'd multiply by 3/2. And in C, where we have x over 7, we could think of that as a 1/7 x. That would also be a stretch by a factor of 7. Okay? Now, this question is asking for the period. So your a value affects your amplitude. We're going to find out our b value affects our period. Because sine and cos and tan are periodic functions. That means that they repeat themselves over a certain interval. So if we look back at our normal graphs that we'd drawn in our notes off to the side the other day, here's our normal sine graph. It has a period of 2 pi because it takes 2 pi before it gets back to where it started. And this shape, which I'll highlight here in green, this shape from there to there repeats itself over and over and over again. And the amount of time or the distance that it takes to repeat itself is 2 pi. Same thing for cos. Cos also has a period of 2 pi. And finally, when we look at tan, our tan graph, how long does it take to repeat? Well, if we take one section of our tan graph, can we see that this sort of thing that almost looks like an x-cubed graph repeats itself over and over and over again? Now, the difference between sine and cos and tan is tan has a period of pi. From -pi/2 to pi/2, that distance is pi. So its period is different than sine and cos. So now when we go to this example, this example says just determine the period of each function, but what we're going towards and we're starting to develop is how to graph these functions. So we're not only going to say what the period is, we're also going to graph these. Okay? So for A, cos of 6x, that's going to be a horizontal compression by 1/6. So if the period was 2 pi, does it make sense that your period is now going to be 1/6 times 2 pi? Because we're going to compress it horizontally. And if we reduce this and simplify this, this just becomes pi/3. So now how do we graph this quickly, easily? Well, we start by making our axes, but instead of marking one period at 2 pi here, since our new period is pi over 3, we'll mark a section there that's pi over 3, and this will be one full period. And just like the axes family splits it into 4 sections, we're going to take that pi over 3, cut it in half, half of pi over 3, pi over 6. Cut that in half, half of pi over 6 is pi over 12, and then we're going to mark this one as well. Since one of these sections is pi over 12, does it make sense when counting that you could call this one 3 pi over 12, which you could reduce to pi over 4 if you wanted to, but you could leave that as 3 pi over 12 as a way of labeling those 4 sections. Notice that each of these functions has a 1 in front of it. That 1 means that the amplitude for the cos is still 1, so it's still going to go up to positive 1 and down to negative 1. Where does a cos graph start? A cos graph always starts at a maximum. And so now that you've got your 4 sections, you can just bounce it from maximum to middle, to minimum, to middle, to maximum. Wow. I got a little low here, but that's okay. So there is the graph of y equals cos 6x. So notice that we didn't take the points from our parent graph and multiply all the x values by 1/6. We sort of used this idea of a period to do it quicker. So if I know that my period was 2 pi and now I'm multiplying by 1/6, my new period is going to be pi over 3. I can mark that new period and divide it into 4 equal sections. So this is going to multiply our x values by 3 over 2. So for the tan graph, the period was pi, and now the period will be 3 over 2 times pi, which will be 3 pi over 2. If we think about our tan graph when we had things before, when we looked at our graph from before, you remember that we had an asymptote here and an asymptote here. Now, if those asymptotes were also multiplied by 3 pi over 2, because this asymptote was at pi over 2, but because you're stretching it by 3 pi over 2, if you multiply that by 3 pi over 2, that will tell us that this asymptote now is at 3 pi over 4. Similarly, this one will be at negative 3 pi over 4. And our graph for tan will still have that same shape between those asymptotes and look like this. Of course, it will continue on either side as well. If you wanted to label one more asymptote, since this period, this from here to here, is 3 pi over 2, if you started at 3 pi over 4 and added 3 pi over 2, get a common denominator of over 4, you'll get your next asymptote will be at 9 pi over 4. Yes? And then for part C, and I'm going to write that x over 7 as 1/7 x. Again, our period of sine was 2 pi. This is going to be a stretch by a factor of 7. So now If you multiply 7 by 2 pi, our period will be 14 pi. And as far as graphing this goes, same thing we did with our cos graph. We start our graph, we make a mark where we're going to have one period, but now one period is 14 pi. If you cut that in half, this will be 7 pi. Cut that in half, and if one of these spaces is 7 pi over 2, this will be 3 7 pi over 2's, which would be 21 pi over 2. Again, the amplitude for this one is 1, so it'll go up to 1 and down to minus 1. And a sine graph starts in the middle, going up. So now that we have our 4 sections, we're going to start in the middle, and then as we go middle to maximum, back to middle, down to minimum, back to middle. And draw a nice curve through all of them. You will lose marks on your final exam if you draw straight lines through them. It has to be a nice curve. Yes? So if this one here, right, this one here is 1 7 pi over 2, this one here will be 3 7 pi over 2's. And if you multiply that fraction, you'll get 21 pi over 2. Because each of these spaces are equal, right? This is like 1, 2, 3, 4. But I have 1 7 pi over 2. 2 7 pi over 2's is going to be just 7 pi. 3 7 pi over 2's. 4 7 pi over 2's will just be 14 pi. So 3, C, and D are the ones that we can do for practice. I also want you to look at the bottom of that page and here we go. So at the bottom of the page, they have this right beside it just to I would like you to write this down in your own words as well. Period of sine and cosine is always going to be 2 pi divided by whatever the b value is. And then your period for tangent is going to be pi divided by your b value. So those are formulas that aren't on your formula sheet. They're really useful though. I mean, it kind of makes sense, like when I have y equals sine of 3x. Using this formula, I can tell right away that my period is going to be 2 pi over 3. Of course, the formula is quick, but it's just based on your compressions. Can you see that that 3 would be a horizontal compression by 1/3? And so if your period was 2 pi, and you now multiply it by 1/3, can you see that you're going to get 2 pi over 3? And so this formula should make sense of where it comes from.